Now, because the concept of self-attention was so revolutionary, let's go into a little more detail about how it works. Now, it's unlikely you'll ever be asked to actually implement this from scratch, but it is useful to know what's really going on, and just for your own curiosity, if nothing else, what is the trick to how these things work these days? So let's go into an example here. So each encoder or decoder, in this case, has a list of embeddings for each token. All right, so we're not really dealing with individual tokens. We're dealing more specifically with their embeddings. So these are converting tokens into vectors in some multi-dimensional space. And we can take the distance between these vectors as some measure of the similarity between those tokens. So words that have a similar meaning tend to cluster together, is what that means. That's what these embedding vectors are. Those are the actual inputs into our self-attention layer. So we'll talk about how that pre-processing works in a bit. But just know that each token is actually a vector. So let's take a couple of examples here. Let's say that we have the phrase, "I read a good novel." Now, in this case, the word novel refers to a book, but novel can be read a different way, right? So attention is a novel idea, is another example here, where novel refers to the concept of something that's new or original. So same token, two different meanings. So self-attention's job is going to be to try to translate each token into its true meaning, if you will. So the token that we end up with, or the vector that we end up with after self-attention, will be something that encapsulates the meaning of a book in this example. And in this example, it might be a vector that more encapsulates the meaning of the concept of original. And when I say encapsulates the meaning, what that really means is where are we in that embedding layer that kind of maps where similar words are to each other. That's where the meanings of each word are basically represented, if you will. So how does this work? Self-attention produces a weighted average of all the token embeddings. So we have many tokens here. I read a good novel. That's 1, 2, 3, 4, 5, 6 tokens if you count the period at the end. The job of self-attention is to compute all of the attention weights between each token. So for the word novel, we have to compute all these weights to I, read, and A, and good, right? So maybe I has a very weak weight. Maybe read has a very strong weight because read and novel is very important to understanding that we're talking about a book in this case. The word A, probably not so important. And good, well, maybe that has, some medium level of importance to determining the real meaning of this token novel, right? So that's what we're representing here. We're focusing on that token novel. The job of self-attention is to compute these attention weights to the other tokens before it. And that block, the magic that happens in self-attention, will output a vector that basically means a book. Similarly over here, novel is looking at the other tokens. Attention is A and idea. It might have a very strong weight with the token idea to figure out that we really mean something original or new here. And as a result of computing all of those weights that we have with the other tokens around it, we might say, well, okay, by novel, we really mean something original here, okay? So another way of saying it here, this results in tokens being tied to other tokens that are important for its context, all right? And this produces a new embedding, like we said, that captures the meaning of that token within its context. So let's review, all right? For every token, we're going to compute attention weights to the other tokens. Self-attention's algorithm will then spit out another embedding. And that embedding, by virtue of where it is in that embedding space, will encapsulate the meaning of that token because it will be near other tokens that mean the same thing. That's it in a nutshell. Now, as for the mechanics of how this all works, again, you're probably not going to be asked to implement this, but it is fun to know about it. Basically, it relies on 3 matrices that are learned through backpropagation. So by training this giant large learning model, part of what you're training are these matrices. They're called the query matrix, the key matrix, and the value matrix. All right. So every token that we're processing is going to get a query, key, and value vector that's just made by multiplying its embedding that we're coming in with against those matrices. So we come up with a token that's been converted to an embedding vector. We multiply that vector with, say, the value matrix, and that gives us a value vector, right? Same thing for key. We multiply that with the key matrix, we get a key vector. We multiply that with the query matrix, we get a query vector. And we do that for every token. With me so far? It's not that hard yet. The next step is we compute a score for each token. And we do this by multiplying its query with each key. So let's look at the word A here. We're going to take the query vector that we got by multiplying it against our learned query matrix, multiply it against the key for each token, okay? And then that produces a score for every individual token that might be associated with this one, all right? We call this scaled dot product attention specifically because there are other ways of doing it, but since we're doing multiplication here, we do that mathematically through what we call a dot product. So this ends up getting called scaled dot product attention. Scaled because we're doing a softmax at the end, by the way. So that basically normalizes everything. So to walk it through again, for every token, let's start with the first one, A. We're going to take its query vector. We're going to multiply that by the key vector, and that gives us a score. We do that for every other token. We take that query, multiply it by the key for good. That gives us a score for good. Take that query, multiply it by the key for novel. That gives us a score for novel. And then we apply softmax just to normalize it all. And now we have our scores for self-attention. You can see this is pretty efficient, right? Now there is one more specific detail, implementation detail here called masked self-attention to talk about as well. And this just prevents us from looking ahead of ourselves, which turns out to be useful. So as you're understanding the spoken word or something you're reading as a human being, you don't really know what's coming ahead of it, right? So this is just a way to make sure that we're restricting ourselves to tokens that came before the token that we're currently analyzing. We do that through a mask. So since we have to do all of this in parallel, we don't really know where we are in the steps of processing this phrase, right? It's all being done at the same time. This mask is what prevents any given token from seeing, quote unquote, seeing other tokens ahead of it. So here we have like a mask where green represents maybe the value 1 and black represents the value 0. So by multiplying each individual token by that mask, we end up masking out any information from tokens that are ahead of us, right? This is something that GPT in particular does, by the way. It's not something that all transformers do. BERT does something similar, but it's a little bit different. It's called masked language modeling, where they're not necessarily masking out tokens in sequence. It could be in a different order, actually. So in this example, the word good wouldn't be affected by the word novel, but the word novel could be affected by good due to how those masks are laid out. Okay, that's just the concept. The implementation details are a little more complicated, and they do vary from model to model, but that's the idea. All right, we're almost done with self-attention. How does this all come together? So for every score that we computed a couple of slides ago, we're going to multiply those scores by the value vector that we got back from multiplying the embedding vector with the value matrix. Okay, so we take each value vector, multiply it by the score, and then we end up with a new product vector. Let's call it Z, just for lack of a better name. So we do that for each token. We take their score, we multiply it by the value, we get a product, okay? And this is all associated with the token that we're processing right now. Remember that we were computing those scores for every other token associated with the token that we're processing. So even though we're just dealing with the word A right now, we're multiplying all the values by all the scores for all the other tokens that haven't been masked out, and we get the product. We then take those products and we add them all up, and that results in our final Z vector here that is basically our embedding that we ended up with at the end of this process. All right. So we do that for every token. So we do it for A, we do it for good, we do it for novel. And this all happens in parallel because there's nothing about this that is not parallelizable. Again, that's the key to making this stuff scale up to the point where it is today. So after doing that, we end up with this Z token that is an embedding for each token that we have to deal with in parallel. So that is our updated embedding for each token. That is representing where in the space of language this token's true meaning lies. And it may seem like magic, but like any neural network, the magic is just in the training and the back propagation and reinforcing weights and biases that lead to correct results at the end of the day during the training process. So it's not magic, but it's pretty cool how it works. At that point, we have something we can feed into the feed-forward neural network sitting on top of the self-attention layer, and off we go. You know, we're well on our way to constructing a complete transformer at this point. So that's self-attention in a nutshell. There is one more implementation detail to talk about, and that's multi-headed self-attention. So if you think back to when we were computing the Q, K, and V vectors, all we did was take the embedding vectors for each token that we started with, we multiplied them by those learned Q, K, and V matrices to get Q, K, and V vectors associated with each token, right? The only thing that's different here with multi-headed self-attention is that we're reshaping those vectors into a matrix. So we stack those on top of individual rows of a matrix. That way we can process them in parallel instead of having to deal with that huge vector all at once. The number of rows we end up with are just called the number of heads. So all that's really happening here is that we're taking potentially very large embedding vectors, they could be thousands of values long, and just rearranging them into these matrices so we can process them in parallel row by row. And it's just another optimization, if you will, that just makes processing faster and allows us to do more stuff in parallel during training.